Okay, the question's been asked. How do we know if a molecule undergoes dipole-dipole intermolecular forces versus dispersion versus hydrogen bonding? And I can go through all three of those. So let's deal with the idea of dispersion. So you'll undergo, two molecules will undergo dispersion if they are both basically non-polar molecules. And if they are polar molecules, then they will undergo dipole-dipole interactions, intermolecular forces, and a special type of dipole-dipole interaction is when the two molecules have an atom attached to a hydrogen that can then be interacting with a third atom if the X atoms are either oxygen, nitrogen, or fluorine, then you end up with a hydrogen bond. So the atom X in this case is either an oxygen, nitrogen, or fluorine on both sides. So you have to have that oxygen, nitrogen, or fluorine bonded to the hydrogen and then interacting on the other side with either another oxygen, nitrogen, or fluorine, and that would give you what we would call hydrogen bonding. Okay. So all of these are going to require, well, except dispersion, except for certain types of dispersion forces, these are all going to require that we draw a Lewis dot structure and convert that to a VSEPR geometry. So for instance, for nonpolar molecules, anything with just a carbon and hydrogen in it will automatically be nonpolar, because a carbon-hydrogen bond is, for the most part, a relatively nonpolar bond. But let's say, for instance, that I had carbon dioxide, and I wanted to know what the strongest intermolecular force is between two carbon dioxide molecules. What I would do is I would say, well, I've got my carbon with my 4 unpaired electrons. I've got my oxygen, each with 6 valence electrons. I'm going to form my carbon-oxygen single bonds, and then I'm going to pair up the other 2 unpaired so that the Lewis dot structure of CO2 is that linear structure. So now to determine whether the molecule is polar or nonpolar, we have to apply the rules. So a molecule is polar if, number 1, it has polar covalent bonds. Carbon and oxygen are polar covalent bonds, so CO2, we'd have a check for the first rule. Oops. For the second rule, you must have a molecular dipole moment. So what does that mean? Basically what that means is that we're going to draw bond dipole moments for each of the polar covalent bonds. So for instance, for carbon, the bond dipole moment would look like this. Now I usually put a plus charge. That means that the carbon is delta plus and the oxygen is delta minus. The head of the arrow is delta minus. The end of the arrow is delta plus. So the carbon's delta plus and the oxygen's delta minus. And then I would draw another dipole moment, another bond dipole over here. Now, if those bond dipoles cancel each other out, then you do not have a molecular dipole moment and the molecule is nonpolar. So in this case, because we have a linear structure, these two cancel each other out. So that means that CO2 is nonpolar. And so CO2 molecules would undergo dispersion forces as their strongest intermolecular force. And a lot of times it's easiest to look at a molecule and determine whether or not it's symmetrical in respect to its bond dipoles. And if it's not symmetrical, then it is going to be polar. So let's look at a couple of examples. The toughest examples sometimes are tetrahedron, but let me work my way up. So let's say I had boron trifluoride. So if I had boron trifluoride, it would have a BF3 molecule. Since boron has only 3 valence electrons, this would be a trigonal planar geometry. So it'd be a 120-degree bond angle there. All 3 fluorines are in the plane of the screen here. And so what would happen is that my boron fluorine bond dipoles would look like this. And since this is a symmetrical molecule, they would actually cancel each other out. So if you added up, let's say, this bond dipole and this bond dipole, you would get one that looks like this, and it would cancel out this one exactly. So BF3 would be a nonpolar molecule as well, and it would have dispersion forces. The tetrahedron are sometimes the most difficult to work with. So let's just start with something like methane. So if you started with methane, you would have a tetrahedron that looks like this. Okay. And our carbon-hydrogen bonds would actually, they would look like this in terms of their individual bond dipoles. And again, if this is a symmetrical structure and all the atoms are the same, they're all going to cancel each other out. So in the case of methane, those are going to cancel, and so you're going to end up with a nonpolar molecule, which means you're going to end up with dispersion forces. Let's say that I put a chlorine on one position, like this. Now the carbon-chlorine bond dipole would look like that. The 3 hydrogens would look like this. And now what would happen is they do not cancel each other out. Because this is not a symmetrical molecule. The bond dipole would look something like this, where this part of the molecule would be delta minus, and around the hydrogens it would be delta plus. So this would be what we would consider to be a polar molecule, and it would undergo dipole-dipole forces. We could go a little bit further. Let's say we had a carbon with 2 fluorines and 2 hydrogens. Remember, this is a tetrahedral structure. So the fluorines would go in this direction, the carbon-fluorine bonds. The carbon-hydrogen bonds would go in this direction. And so they would not cancel, because in a tetrahedron, all 4 atoms have to be the same to cancel. In this case, the net dipole would go in this direction, with this direction of the molecule being delta minus, and this part of the molecule being delta plus. So this would be a polar molecule and would therefore undergo dipole-dipole forces. Fine. Something like ammonia, where you have a nitrogen attached to 3 hydrogens, and then you would have your lone pair. In doing dipole moments, the lone pairs are never counted, so you just ignore them. So in this case, we would have our bond dipoles would look like this, with the hydrogens being slightly positive and the nitrogen being slightly negative. So the net dipole then would go in this direction with the delta minus, this one being delta plus, this one being delta plus, and this one being delta plus. So ammonia obviously is a polar molecule, and it would undergo dipole-dipole forces. Okay, so you have to go from the Lewis dot structure to a VSEPR geometry before you can determine whether a molecule is polar or nonpolar. Okay, and so for instance, the example that I use is, let's say, water. So just drawing the Lewis dot structure isn't enough, because I can oftentimes trick students into drawing water like this, and they go, oh well, but my bond dipoles cancel out, so water's not polar. And then I say, well, what did you just say? Water's not polar. Of course it's polar, because the Lewis dot structure then has to be changed into the tetrahedron, and in that case the bond dipoles do not cancel, so that the oxygen part of the molecule is delta minus and the hydrogen is delta plus. Okay, so the easiest thing to do is when we look at a structure, unless it's perfectly symmetrical in terms of its VSEPR geometry, meaning that there's an atom at each position, the molecule would be polar. If it was symmetrical with an atom at each, having different atoms at the positions, then it would be unsymmetrical, and it would be, in that case, polar. Now, the question oftentimes comes, what does it mean to be a polar molecule? And what it means to be a polar molecule is that you have an unequal electron density around the surface of the molecule. And let me show you an example of that. Okay. So on my iPad, let me draw a carbon with, let me draw a methane molecule. So there's a methane molecule, and I can put it into 3 dimensions. So there's my tetrahedral methane molecule. Now, if I take this molecule and I look at its surface, the charge on its surface, what you can see is that throughout the methane molecule, the color never changes. And what that means is there's the same charge on all of those hydrogens. Well, if you have the same charge on all those hydrogens, you can't be polar. You have to have a part of the molecule surface that's delta plus and part that's delta minus. So let me go back to my methane and go back to my editor, and let's say I'm going to go ahead and replace one of these hydrogens with a chlorine. And now I'll go ahead, and again, here's my structure with my big chlorine atom, and now I go to put a surface on it. What you can now see is that the surface of the molecule has different charges. It's got a delta minus where the yellow chlorine is, and it has a delta plus where the hydrogens are. And so now for this molecule having different charges, what it would look like is the chlorine would again be a delta minus part of the molecule. The hydrogens would be where the delta plus is. So if I now took 2 what is called methyl chlorides, and I put them together, they would line up so that the delta minus part of the molecule, of one molecule, was attracted to the delta positive charge of the other. And so that would be your dipole force, intermolecular force. Okay, and then we can do another one here. So let me take my molecule and let's edit it. Let's put in 2 fluorines. Now, in that structure, you could say it's a tetrahedron, so the fluorines are not going to cancel each other out, right? So here's my tetrahedral structure with my hydrogens and my fluorines. And now what I can do is, oh good, it's not in the database, so let me change the fluorines to chlorines because I'm sure they're in the database. Okay, so again, here is my molecule with my chlorines, and now you can see that where the green and yellow, that's the delta minus part of the molecule, and the blues are where the delta positive is. So again, why is this molecule polar? It's because the tetrahedron doesn't have all 4 atoms the same. If you don't believe me, let's make the rest of these hydrogens chlorines. And now let's put the electron densities. And so here is CCl4. And what you can see with CCl4 is that all of the atoms have the same shading of green. And there is no delta plus or delta minus difference on the surface. So actually, CCl4, carbon tetrachloride, is actually nonpolar. And it would undergo dispersion forces despite the fact that it has a polar carbon-chlorine bond. But in this case, the CCl4 molecule, all 4 of the chlorines in the tetrahedron would cancel each other out. Okay? So that's what it means to be a polar molecule. Now for NH3, I can go back and draw that. I'm just going to delete my molecule. I'm going to put a nitrogen, and I'm going to make that a hydrogen, and then here is ammonia. So here's the structure of ammonia. I can go ahead and flip it around. So there is my ammonia molecule. And you can see that what you can't see actually is you can't see the lone pairs that are up here. But in a tetrahedral structure, you've got lone pairs and then the 3 hydrogens. Since if there was another hydrogen there, it might be nonpolar, although then it would be ionic. But in this case, it's not symmetrical. All the bond dipoles are pointing towards ammonia. So if I looked at its charge, what you can see is that the hydrogens are the really dark blue, and the nitrogen is the red, which is a really delta minus charge. So ammonia clearly is a much more polar molecule because the nitrogen-hydrogen bond is a much more polar covalent bond. And so what would happen with ammonia is that now one of the hydrogens attached to the ammonia could hydrogen bond with this nitrogen, so that now I have a situation where I've got an O, N, or F covalently bonded to a hydrogen, which is then electrostatically attracted to an O, N, or F. And so this would be what we would call our hydrogen bond. Okay. Now, why is it O, N, and F are the only ones that can form hydrogen bonds? Because if I think about forming that bond, the covalent bond to hydrogen, I want the hydrogen to have the most delta positive it can be, and the only way to get the hydrogen with the most delta positive is to have one of the 3 most electronegative elements attached to that hydrogen, and that's where the O, N, and F come into play. Okay, so that's kind of a abbreviated look at how we determine whether something is polar, non-polar, whether it can hydrogen bond. But we have to take a Lewis dot structure and we have to convert that then to a Vesper geometry. And in the Vesper geometry, a polar molecule has to have polar covalent bonds, and it also has to have the molecular dipole moment not equal 0. So it needs to have a molecular dipole moment. Okay. So if you have any questions, you can email me or post a follow-up question on Piazza.